In this videotape, we're going to look at word problems which result in one rational equation, an equation with fractions. For the first problem, we're going to look at this one over here. By the way, before you start this tape, if you do not have a problem sheet, you should shut off the machine and get a sheet from the person running the lab. Okay, problem one. One number is 5 times another. The sum of their reciprocals is 2/5. Find the numbers. Okay, so the first thing we're going to do is to assign a variable to one of the numbers. Let's say let x equal one of the numbers, a smaller number. And then the other number is 5 times that, so 5x equals the other number. One number is 5 times another. So one of the numbers is x and the other one is 5x. The sum of their reciprocals is 2/5. Okay, the reciprocal of the number x is 1 over x. The reciprocal of 5x is 1 over 5x. The sum of their reciprocals is 2/5. Okay, we're looking to find the numbers. We would like to solve this equation for x. It is an equation involving fractions. I find the easiest way to handle such an equation is to multiply both sides of the equation by the LCD of the lowest common denominator here, and in that way clear fractions. Okay, so in this case we have x, 5x, and 5 for the denominator, so 5x. Multiplying both sides of the equation by 5x with clear fractions. Each term gets multiplied by the 5x. It's 1 over x times 5x plus 1 over 5x times 5x equals 2/5 times 5x. 1 over x times 5x, the x's cancel, we have 5, plus here, the 5x's cancel, plus 1. Don't make a mistake and write 0. 5x, you divide numerator and denominator by 5x, you just get 1. Equals 2/5 times 5x. The 5's cancel, we get equals 2x. 6 is equal to 2x. Dividing both sides by 2, x is equal to 3. Okay? The question asks you to find the numbers. So the answer would be the numbers are x and 5x. If x is 3, the numbers are 3 and 15. One number is 5 times the other. Now, we must check in the words of the problem. One number is 5 times another. The sum of their reciprocals is supposed to be 2/5. Okay, the reciprocal of 3, that's 1/3. The reciprocal of 15, that's 1/15. And combining, we can combine over the lowest common denominator here, which is 15. 1/15, 1/3, multiplying top and bottom by 5 gives us 5/15. 5/15 plus 1/15, that's 6/15. And 6/15 can be reduced if you divide numerator and denominator by 3. 6 divided by 3, that's 2. 15 divided by 3, that's 5. And it checks out. The sum of their reciprocals is 2/5. Okay? Two numbers, one is 5 times the other. The sum of the reciprocals is 2/5. The second problem on our sheet is a distance problem or motion problem. The speed of a boat in still water is 8 miles per hour. It travels 30 miles downstream with the current in the same time it takes to travel 18 miles upstream when it's against the current. Find the speed of the current. Okay, now this problem may seem a little unusual to you. It's a little more difficult to set up than the reciprocal problem that we just worked out. Certainly we're looking for the speed of the current, so we could let x equal the speed of the current. Of course, that's in the miles per hour, the common unit that we're dealing with here. Okay, in distance problems of this form, it's helpful sometimes to make a table to collect all the information that we have. You'll remember that in distance problems, distance is equal to rate times time, d is equal to r times t. For example, if somebody is traveling, at 20 miles per hour for 2 hours, at the end of those 2 hours, you would expect him to have traveled 40 miles. 20 miles per hour times 2 hours, the hours cancel, you get 40 miles. Distance is rate times time. Okay, so we need to know these quantities. And I'm going to make one row of the table for upstream and one for downstream. And I'm going to make a column for the distance traveled, the rate, and the time, just to collect the information that we've been given in the problem. Okay, now, it travels 30 miles downstream in the same time it takes to travel 18 miles upstream. So the distance traveled upstream, that's 18 miles. And downstream, that's 30 miles. The rate. Okay, now the speed of the boat in still water is 8 miles per hour. When it's going downstream, you have the speed of the boat, and you're going with the current, and you add on the speed of the current. However, when you're going upstream, you're against the current. You must subtract from the current, the speed of the current, from the 8 miles per hour. In other words, you're 8 miles per hour minus the speed of the current when you're going upstream. Downstream, you're going with the current. Upstream, you're going against the current. So the rate, the speed here, for upstream, I'm going to write 8 minus x, the 8 miles per hour for the still water, minus the speed of the current. For downstream, I'm going to write 8 plus x. The speed of the current is added to the speed of the boat in still water. Okay, now, if distance is rate times time, time is distance over rate. T is equal to d over r. D equals r times t, dividing both sides by r. T is equal to d over r. So, the time upstream would be the distance over the rate, 18 over 8 minus x, while the time for the downstream row here would be the distance over the rate, 30 over 8 plus x. Okay, now we have filled everything into our table, and we look at the problem, and we see that the key here is that it travels 30 miles downstream in the same time it takes to travel 18 miles upstream. That is, the time going downstream is equal to the time going upstream. So we set the two times equal to each other. Time going downstream, 30 over 8 plus x. We set that equal to 18 over 8 minus x, giving rise, once again, to a rational equation, which we intend to solve. All right, let's look at it again. It travels 18 miles upstream. The speed, when it's traveling 18 miles upstream, the speed is 8 minus x, because you're going against the current. You take the current away from the speed of the boat in still water. And time is distance over rate. Here, 30 miles downstream, going at 8 plus x miles per hour, the speed of the boat in still water plus the speed of the current, the time, distance over rate, 30 over 8 plus x. And it travels at 30 miles downstream in the same time it takes to travel the 18 miles upstream, so we set the two times equal to each other. We can multiply both sides of this equation by the LCD, which happens to be the product of the denominators here. That is, multiply both sides by 8 plus x times 8 minus x. Okay, on the left here, the 8 plus x is canceled. We get 30 times 8 minus x. And on the right side, the 8 minus x is canceled. We have 18 times 8 plus x. By the way, some of you may say, well, why can't I simply cross multiply? If you have seen that before, by that I mean if you have like two fractions, a over b equal to c over d. Okay, it is true that if you cross multiply, AD equals BC. Okay, we get the same effect here as if we multiply both sides by BD. Okay, you get AD equals BC. Okay, there's nothing wrong with cross multiplying as long as you realize that it is only when you have one fraction equal to another fraction. If you had, say, like we had in the last problems, the sum of two fractions equal to a third fraction, then you can't use cross multiplying. And you must multiply both sides by the LCD. Here you sort of have a choice, only because you have one fraction equal to another. Okay, so let's distribute the 30 through the parentheses, and we get 240 minus 30x equals 18 times 8, that's 144, plus 8x. And, plus 18x. 240 minus 30x is 144 plus 18x. Okay, now we can add 30x to both sides. 240 is equal to 144 plus 48x. Subtracting 144 from both sides. 48x equals 96. And then dividing both sides by 48. X comes out just equal to 2. X, you'll remember, is the speed of the current. Okay, so our answer is the speed of the current, that's what you asked for, is 2 miles per hour. Okay, let's just check this out in the words of the problem. We have upstream and downstream. Upstream, you were going 18 miles. The speed is 8 minus x, you'll remember, because you were going against the current. The speed would be 8 minus 2, 6 miles per hour. How long did that take? Time is distance over rate. 18 miles per hour. 18 miles divided by 6 miles per hour gives us 3 hours. In other words, if you traveled 6 miles per hour for 3 hours, you would cover the 18 miles. Well, according to the problem, same time to go upstream as downstream, so we assume that we're also going downstream for 3 hours. Now, the rate going downstream is 8 plus x. 8 plus x, 8 plus 2, 10 miles per hour. So we're going to be going downstream 3 hours, 10 miles per hour. We should be able to go 30 miles downstream, which is, of course, what we would expect. So the whole thing does seem to check out. The third problem, 2 people working together can complete a job in 12 hours. If one works 3 times as fast as the other, how long would it take the slower person to do the job alone? This is also a different type of problem. If you haven't seen one like this, you probably would not be able to handle it the first time around. But once you do see it, and you understand that you should be able to handle work problems like this without any difficulty. I find that an easy way to handle the problem is to consider the work done in 1 hour. Okay, to basically think of a 1 hour time period. See, the key here is that we're going to assume that these people are working at a constant rate. Okay? If somebody takes 4 hours to do a job, we're assuming that the first hour he works as fast as in the second hour, or the third hour, or the fourth hour. He accomplishes the same amount of work in each hour. He is working at a uniform rate. Okay, now, what I want to do here is to consider the work done by each person in 1 hour. Okay, we can, we're going to have to set up some sort of unknowns here. We have 2 people. I'm interested in how long it takes the slower person to do the job. Be careful here. One person, let's say, is going to finish a job in X hours alone, and the other one in 3X hours working alone, because one person works 3 times as fast as the other. The faster person does it in X hours. The slower person does it in 3X hours. So X is the time for the faster person to do the job alone. And 3X is the time, that is the number of hours, okay, for the slower person to do the job alone. For example, if X were 2, the faster person would do the entire job in 2 hours alone. The slower person would take 6 hours working alone. 3X, okay, goes for the slower person. It takes him longer. Okay, the faster person is working the one person works 3 times as fast as the other. All right. Now, if it would take a person, say, 6 hours to do the entire job working alone, then you could assume that in 1 hour he would do 1/6 of the job. In 3 hours he would do 3/6 of the job, or half the job. In other words, we're trying to consider the amount of work done by a person in 1 hour. If it takes him 6 hours to do the whole job, in 1 hour he does 1/6 of the entire job. We're assuming that he's working at a constant rate. So in the first hour he does the same as in the second hour, he does the same as in the third hour, and so on. Okay, so over here we are assuming that one person does it in X hours working alone and the other does it in 3X hours working alone. Okay, in 1 hour. Okay, we want to consider the amount done by the faster person. We're going to add the amount done by the slower person. And we're going to get the total amount done in 1 hour. Okay, the faster person does the job in X hours working alone. Okay, let's pretend he was doing it in 6 hours working alone. Therefore, in 1 hour he would do 1/6 of the job. If it takes him X hours to do the entire job, in 1 hour he does 1/X of the job. If it was 6 hours for the whole job, in 1 hour he would do 1/6. If it's X hours for the whole job, in 1 hour he does 1/X of the whole job. Similarly, the slower person, let's say X was 6, it would take him 18 hours to finish the job alone. In 1 hour he would only do 1/18 of the entire job. Or if it takes him 3X to finish the job alone, he would do 1/3X of that in 1 hour. This is the amount done by the faster person in 1 hour, the amount done by the slower person in 1 hour. Let's see the total amount done in 1 hour. Together, they complete the whole job in 12 hours. Together, in 1 hour, they will therefore do 1/12 of the job. And here we have our rational equation that we were looking for. Let's go over it again. The faster person does the whole job in X hours. In 1 hour, he does 1/X of the job. The slower person does the whole job in 3X hours. In 1 hour, he does 1/3X of the job. Together, they would finish the whole job in 12 hours. So in 1 hour, they would do 1/12 of the job. Okay, so to solve this equation for X, all we'd have to do is multiply both sides by the LCD, which is, in this case, 12X. 12x times 1 over x, the x's cancel, we get 12. 12x times 1 over 3x, the x's cancel, 3 into 12 goes 4. And 12x times 1 over 12, the 12's cancel, we get x. We get 16 equals x. Okay, 16 hours for the faster person to do the job, working alone. 16 times 3, 48 hours for the slower person to do the job alone. The question was, how long would it take the slower person to do the job alone? So the answer, slower person would take 48 hours alone. It does seem to be consistent here. Naturally, you would expect that together they could do the job in a time less than the individual time on either of them. In other words, he could do it 16 hours alone, 48 hours alone for him. You would expect together they should be able to beat, say, the 16 hours. Otherwise, why would he need them, right? So 12 hours together does make a certain amount of sense. And you can, of course, check this out. If the slower person does the whole job in 48 hours, in 1 hour he does 1/48 of the job. The faster person does the entire job in 16 hours. In 1 hour he does 1/16 of the job. So in 1 hour they would have accomplished 1/16 plus 1/48, or 3/48 plus 1/48, combining over 48s, 4/48, or 1/12 of the total job in 1 hour, and therefore they would finish together in 12 hours, which is what we would expect. And that brings us to the end of this tape.